Congratulations. Look forward to seeing you running. With that, let's hear from Joe.
Let's give him another wave.
Microphone check. How are we doing? Maybe a little bit louder for you guys in the back.
Thank you. We're good.
How about now?
Great. Good.
All right. My next car gets 100 miles per gallon. So I'm Joe Justice, the team lead of WIKISPEED. And WIKISPEED is a distributed collaborative team. It's a group of folks working nights and weekends, and a few of them full-time, but all volunteer, to produce the future of automotive transportation. What does that possibly have to do with Agile, Lean, and Scrum? We use Agile, Lean, and Scrum exactly as it applies to software teams to build our vehicle. And it just so turns out that we learned a whole lot when we tried to port those practices over. And I'll talk about what went well and what didn't go well, and what our next steps are, and what the future of this technique might be. So first, I'm Joe Justice. I'm a software developer and Agile Lean Scrum coach in the Seattle area. I lived in Denver, Colorado when the events in this story started, and I've only been in the Seattle area about 3 years now. So I'm by no means a public speaker. I'm a software dev. But I've had the luck of being in Team WIKISPEED, and actually the team lead of WIKISPEED, which on its own is an amazing story that you'll get to know all about. In 2008, the Progressive Insurance Automotive XPRIZE was announced. It was a challenge to see, is it even possible to build a 100 mile per gallon car that met road legal spec? Up until that time, that had never existed. What we had were things that were kind of like bobsleds. And the one driver, no passengers, would lay down and scoot at 25 miles an hour. And then it would coast down to 5 miles an hour. And they'd fire the engine 5 times, get back up to 25 miles an hour, and keep going in a temperature-controlled velodrome, slowly turning left. And they got well over 100 miles per gallon. We didn't have cars that sat 4 adults, had at least 10 cubic feet of trunk capacity, had air conditioning, defrost, heat, and a stereo, 4 wheels, at least a 200-mile range, that met 100 miles per gallon. It did not exist. The XPRIZE had just come off an enormous success. They had launched the Space Exploration XPRIZE, or the Anasari XPRIZE. And that was a challenge to get to a certain altitude, determined to be outer space, land, and get back within 24 hours. And they put a $10 million prize purse on it. It went well. A team won. A team funded by Paul Allen, Scaled Composites, using a Burt Rutan design. And they had successfully commercialized spaceflight. So if a researcher, for example, had an experiment that needed to be done in true zero-G on the actual, and not simulated, or on the actual other side of the atmosphere, they now had it out without partnering with big government, which can be difficult, time-consuming, or impossible, depending on your research aims. They had now commercialized space travel. They said, what can we do next? How about changing the world, saving the world with 100 mile per gallon cars? And that was announced in 2008. I was one of those guys in college that zipped around in a turbocharged Honda with a huge wing on the back. I was one of those guys. I was going to school at the University of Wyoming, and mountain racing was what was in there. And we would shoot down mountain passes at night, and that's what we thought was the neatest thing in the world. It turned out I was much more interested, and actually a little bit better, at the engineering of trying to go a little faster. And I actually wasn't that fast of a driver. So I ended up more working on things and calculating things than driving. So it was a little safer too, maybe. And I realized that if I wanted to go a whole lot faster, I wanted my car to be lighter. And I had stripped, as they would say, reduced to race weight, my little Honda, It had no headliner, it had one speaker, because he still had to have a stereo, but it just had one speaker. And replaced the seats with these lighter seats. And still, I wanted to go a whole lot faster. And that required a whole new chassis. And what was popular when I was in college was road racing. So it wasn't going to the drag strip. It had to be road legal. That was important. That's where the cool factor was. And so I was researching lighter and lighter weight chassis and said, man, wouldn't it be awesome if I could make my own car? Well, I graduated from college, and my first shop was an Agile-only shop. And so I didn't know anything about Agile, Lean, and Scrum. I hadn't seen another way of doing business. And I was quickly poached by a consulting company, and I was deployed on a 50-person project, and we were writing a titling and registration system for the Department of Motor Vehicles. So the part I was responsible for, give it to the new guy, was read the Code of Federal Regulations, which if it were printed out, is about 1.5 inches thick. And I wrote the rules engine to say, or one of the people who wrote the rules engine, to say, if someone walks into the DMV and hands you a piece of paper, how does the person behind the counter know it's legitimate? And they can put plates on that thing. How do they know it's road legal? I had to learn all about it. It took hundreds and hundreds and hundreds of person hours. And at the end, I realized I knew how to register myself as an automotive manufacturer. And so now you have this person who's passionate about driving fast and lightweight cars. That was just my personal take on it. Because the lighter a car is, if you don't give up safety, there's really no downside. Your tires last longer, you use less fuel to go a distance, you can accelerate faster, you can brake sooner with the same amount of brakes, the same amount of engine. So lightness, if you don't lose safety, is really the best way. And so I was fascinated by it, and now I could make my own road legal cars. And all I knew was Agile, Lean, and Scrum. So it's 2006 now. I start prototyping my first 2 chassis. And they're coming along, they're really lightweight, but they made the whole time to road legal spec. They're not complete, but they're coming along, and they're very light for meeting road legal spec. And the Progressive Insurance Automotive XPRIZE announcement comes out. And I say, I know lightness is part of the equation for fuel efficiency, so maybe I'm on the right track. Maybe I've got a shot at this $10 million prize to revolutionize automotive transportation, or at least be a big part of it. So I spend the next 3 months writing a piece of software that simulates the EPA city and highway driving cycles. And so it takes a whole bunch of data in, and it outputs per second how much fuel is consumed on those driving cycles, and then gives you your fuel economy score the same way you see it on the window sticker of any car that we would go buy right now. It says the EPA city driving score is, the EPA highway driving score is, the UDDS and HWFET driving cycle scores. And I put in a whole bunch of existing cars that were on the road now, and refined the algorithm until I was reliably getting the scores the EPA got. And then I put in these chassis I've been working on. And they came back with 70 miles per gallon in simulation. I said, maybe I can do it. And so I talked to my wife, and I took my entire savings, I was still pretty recently out of college, $5,000, and I put it towards the entrance fee in the Progressive Insurance Automotive XPRIZE. She encouraged me, saying, if you don't do it, you'll always wonder what had happened. Try it. And so I did. And everything I did, I put on a blog. And I asked a lot of silly beginner questions on the blog. Hey, how come it won't start when this happens? I asked a lot of complex questions on the blog. And people started to comment, and people started to stop by the garage and see what I was up to as I tried to build out these not complete chassis into something that could contend in the XPRIZE. And I had 1.25 years to do it. And something I totally didn't expect to happen happened. They began to stay and help. I hadn't relied on that at all. I hadn't counted on that at all. It would have been very difficult to get very far had they not. And we passed every technical deliverable for the Progressive Insurance Automotive XPRIZE and got this logo. This logo meant we're a finalist. It has these green laurels on it. It meant we were going to the final events at Michigan International Speedway to compete against 136 cars brought from all over the world, most of them funded by millions of dollars. When we became a finalist, there was still a lot more work to do, and I talked to my wife again. We had saved up a down payment for a home in Seattle, and I had just been told I'm 12 cars away from winning $10 million. Well, right now it's the whole team. There's now 44 of us in 4 countries working on this car using Agile, Lean, and Scrum, which I'll talk all about in a minute. And we took our house down payment and invested it into the company, and we had a startup capital of $130K. All other funds came from donations through our website, through PayPal. We had donations as big as $35K and as small as $1. And they all made an enormous difference and got us to the finals. I'll put back a slide. So at that time I was in Denver, Colorado, before the finals on that little star. That was my garage, and it was just me in the beginning. And there were 136 cars from many, many nations and many, many states. When we became a finalist, I had just relocated to Seattle, Washington, and the team had grown dramatically. And then we went to Michigan International Speedway. Front and center is Al Unser Jr., 2-time Indianapolis 500 champion. He was the hired driver of a team competing against us. Al loved how quickly our team worked together to solve problems and continued to iterate the car even at the racetrack. He hadn't seen that type of thing before. And he spent a lot of time hanging out with our team, and we got to take this great picture among others. 16 of us flew out to Michigan International Speedway to participate in campaigning the car there. Most of us, paid for our own tickets and took unpaid vacation to be there because we thought this was something worth doing. Ultimately, we tied for 10th place in the mainstream class. That meant we didn't get $10 million, which by that time the XPRIZE had grown to be 3 classes, and the prize purse was divided over all 3. So the prize purse from the mainstream class, which had started at $10 million, was now $5 million, which was still an amazing prize purse to try to compete for. And to be 10 steps away from that was a novel experience. What we got as finalists is several tens of thousands of dollars in road legal certification and testing from Roush Industries, who does the road legal certification and testing for many domestic manufacturers, and I believe also Mercedes-Benz. We also received an enormous amount of positive press. We were in Popular Science, Popular Mechanics, Wired Magazine, Autoblog Green, the Discovery Channel in Canada, the National Geographic Channel worldwide, and our team grew to 56 members in 6 countries by losing. So we said, what are we going to do next? How about we see what parts of our car are applicable to a road legal car that we can productize and make available to people. We have a car that posted in testing as part of the XPRIZE 104 miles per gallon on the EPA city cycle, in simulation of that cycle in conjunction with the XPRIZE, and 114 miles per gallon on the HWFET highway cycle. That's pretty amazing. But it didn't clinch the lead. We got 10th, tied for 10th in the mainstream class. We learned a whole lot and then decided to do something enormous. Here's the learned a whole lot part. This is that car underneath that orange shoebox. So that orange body had the aerodynamic profile we cared about. Here, I'll click that. It has NACA airfoils on the front and rear. You can't see the rear from this angle, but it's actually identical to the front. NACA is the predecessor to NASA. The car is very low and has the aerodynamic profile we care about, but it's not very pretty. I call it the orange shoebox. Lovingly, but it's correct. Underneath the orange shoebox, we have a set of modules. Modules like we would do in software, that we use contract-first design, like you would a web service. This is completely novel to automotive manufacturers. Automotive manufacturers talk about and do think in terms of modules, that are welded together before the machine leaves the factory, and then are produced on machines with dies that cost more than $1 million a piece, so to change the module requires a several $1 million ramp up. Let's talk about what's different. Here is our front crush structure. It's 6061 T6 aluminum, and it's bolted with 4 structural bolts to the front of the vehicle. That's our contract. Anything that meets that bolt pattern and can channel the structure into the load-bearing members on the chassis behind it is fair game to attach there. That's version 3 of our front crush structure, which is the way we campaigned it in the XPRIZE. This is the car as it campaigned in the XPRIZE. That means when we made an innovation in our front crush structure, we didn't have to build a new car. We could plug it into the existing car. The suspension plates on all 4 corners are, again, a contract. It uses 8 structural lugs, which are the same types of lugs that hold the wheels on the car. So it's known tech. It's the same way all the weight transfer of a vehicle is currently maintained, but we have the entire suspension system attached to one. Right here we have what they call McPherson strut suspension at all 4 corners. The car as it sits right there is 10 minutes away from having double wishbone suspension at all 4 corners, or any other suspension type we care about. And it's adjustable. The car's heading this way. It's adjustable in caster, toe, camber, wheelbase, and track, individually per wheel. For those of you who aren't car nuts, that's very rare. That level of configurability is uncommon. The entire interior in the race car version was an aluminum bathtub that lifts out. We were campaigning in the 4-seat class of the XPRIZE. We also had a 2-seat interior for testing, and we could swap them out like you're lifting a flower pot out of another flower pot. The entire engine rolls out of the back of the car, and by the entire engine, I mean the entire powertrain, with its transmission, its fuel tank, its cooling system. Roll out in the time it takes to change a tire while it's running. What that let us do is have it let us have one engine on a test bench going through the paces and being evaluated, just like we would with automated regressing tests and software. And another engine in the car out doing testing, pull them in, switch the 2, and test in the chassis. And we were able to then evolve these systems independently of each other. If a game-changing battery technology had come about, we're an all-gasoline setup. We use just very little gasoline. If a game-changing battery technology had come about 2 weeks before the XPRIZE, only teams that were already working with an electric drivetrain that was compatible with that new battery chemistry would be able to take advantage of it and go on to win. But we could too, because we could switch and integrate a new module in minutes. And it would take us about a weekend to take an existing engine technology and compartmentalize it in one of our engine modules. So that was our green card. That was our get-out-of-jail-free mechanism for the XPRIZE, is that we could change so quickly and so inexpensively. If we had changed to an electric drivetrain, which we didn't need to do, we wouldn't have had to rebuild our braking system, our crush structures, our steering system, our seatbelt system, because they're all independent assemblies. Just like when we're writing software, if we want to incorporate a new security protocol, we definitely don't want to be changing the type of database we're talking to. Those are loosely coupled. Those shouldn't affect each other. We took the same concept to physical goods. Here's our suspension quarters taken off the car. This is actually a version just after the XPRIZE. You can see the aluminum plates, the McPherson strut suspension, our lower wishbone, and our braking system. The entire braking system is controlled by a pedal plate, which is loosely coupled. We used 4-channel ABS braking system on our XPRIZE race car. And that was all on one plate on the front of the car. So we could change it all at once without having to change the rest. Here's just the chassis of the car. If we're thinking of this in terms of contract first development, this is the contract where all the other modules connect. Here you see 4 dummies in the car, and this is finite element analysis of impact scenarios. Here we see front stress loading on the vehicle, and we see how 4 people sit in this chassis that the modules connect to. This is where things get really interesting. This blue box is the deformable barrier that the NHTSA and IIHS use when they do side impact testing. This blue box is the same size and shape, and this is our finite element analysis of the side impact test. In the side impact test, that blue box is attached to a sled that's weighted to 5,500 pounds. That's the weight of a medium-duty pickup truck with some load in it. It's then towed into the side of your vehicle at 35 miles an hour. It's a devastating test. It's often lethal to the simulated occupants. What they look for is penetration into the cabin, how many inches of penetration. And then they look at the pulse of the energy wave going through the occupants to verify it's not going to damage internal organs, so that the energy is absorbed at the correct rate of speed. With the WIKISPEED chassis, in this picture from finite element analysis, red means peak stress, the area of the chassis that's stretched the most. If this chassis were flipped this way, so you saw the impact face, it's all red. But we see something much more interesting looking at the other side. Again, red is peak stress. There's red on the complete opposite side of the chassis from the impact side. That's not true just in side impact, but in frontal and even offset frontal impact. What that means is, in a normal chassis, when the car's hit, that part it hits has to be heavy enough, thick enough, strong enough, and braced enough to take that entire impact without having the 5,500-pound rolling medium-duty truck crush into the car. Our entire car absorbs the weight because we have this simple geometric shape. Wow. That was a happy accident. We were trying to be as rigid as possible without having to do very complex operations. And so we took the lightest thing that was rigid enough to hold all four wheels and iterated to make it simpler and simpler and simpler and simpler until we ended up on this rectangle, essentially, this buttressed, three-dimensional rectangle. And it turns out it works just like an I-beam when it comes to impact, where you have thick flanges bearing load and a thin web. Well, the thin web is essentially the passenger area. And it works, that means when it's hit, until its fail strength, it behaves like one solid ingot of aluminum, absorbing enormously high impacts. Then the energy absorption, we talked about the pulse of the impact, also met all safety regs. This is, to my knowledge, as far as anyone has publicly spoken about, the lightest chassis ever made to achieve a 5-star crash rating equivalency, front, side, rear, and when the roll hoops are attached, roof crush and rollover. You guys are awesome. So I get really excited about it, of course, because I'm a car guy. But you guys seem to get it, that we're doing something really novel, and yet we're not really well funded, like I said. We're not really that big, like I said. So how is it that we're hitting so high above our weight class and doing novel, new, interesting, game-changing technologies with far fewer resources and people than anyone else who's been a player in the game for a long time? Well, that's a story many of us are familiar with from being on Agile, Lean, and Scrum teams. Let's talk about how that worked with physical manufacturing. So right after the XPRIZE, our team had grown and we had all this positive publicity. And we said, let's see if we can bring some parts of this, the parts that might make sense, to market and make it available. We have a car that is 114 miles per gallon on the highway that meets road legal spec. Let's share. So we had a CNC machine cut out of foam, a full-size new car body. We concentrated our efforts on CAD and had several team members who were CAD savvy draw up a bunch of different car designs. Here being machined is what we called in the team Car Body 2. And there I am hand sanding it, and Lisa Ford is hand sanding it. We're in a 3-bay garage in Hillsdale, Michigan, one of the WIKISPEED sites. At this point, we have more than 70 volunteers in 6 countries, and we have multiple locations now. So we have people working out of their spare bedrooms, their garages, their office space, and sending parts in to where I am in Seattle, Washington for testing and integration. And then we even have a full other 3-bay garage set making a whole other car in Michigan according to the same spec after the XPRIZE. There's our sprint planning board. We modeled it. Right after a Kanban board, the very limited set of swim lanes and columns that Kanban recommends. And that worked great for us for the Hillsdale, Michigan shop. And if we could read those notes, they say things like, sand the body, which we're doing. Then we laid it up in structural carbon fiber and attached polycarbonate windows. Now, some of you might say, hey, wait a minute. Structural carbon fiber is reserved for aerospace and the most exotic high-end automobiles. How can you possibly even afford that? We really wanted to use carbon fiber. For its energy absorption capabilities, it's one of the best materials you could possibly use when you then factor in its weight as well. But it's really expensive stuff. What I found, though, is the material itself actually isn't very expensive. It's the knowledge of how to use it. The consulting rates, if you were to think about it that way, it's really expensive for people that know how to make structural stuff out of carbon. So I put myself through composite school. I took a few weeks off software development and consulting and went to composite school and came back. And this is the first structural carbon fiber layup in Hillsdale, Michigan, which the Chamber of Commerce was thrilled about because now there are 7 people in Hillsdale, Michigan that know how to do structural carbon fiber layup. So now there's this skills building going on where people are getting smarter and smarter with the top-notch methodology and the top-notch materials and processes. We then took our same XPRIZE mechanicals, but under this new, pretty structural carbon fiber body to the largest auto show in the world. Usually, teeny little companies like us don't get in. The year before, 2010, this is January 2011, so this just happened now. In January 2010, though, they had a few small companies, a few electric car companies in the basement, and they called it Electric Alley. A lot of reporters went down there because they weren't so interested in what the Big Three was doing right then. The Big Three wasn't doing very well right then, and the reporters wanted to see the new, interesting stuff and went down into the basement and visited Electric Alley. And in 2011, the auto show realized that that might be true again, and they solicited us and put us on the main floor between Ford and Chevrolet. Luckily, we had a beautiful car. Rob Moorbacher penned the car. He's Moore Composites is his day job, and he makes unmanned composite airplanes and then large-scale remote control aircraft. And he designs them in CAD and lays them up in carbon. So he's used to designing things that are then able to be made in the real world. And he designed this car body from his home in Germantown, Maryland, and emailed the CAD to me. I loved it. He emailed many, and we shared them across the entire team. And this is the one the team chose, Car Body 2, as we called it in team. And I'd never met the guy. That's part of this distributed collaborative team that we go into. I built this person's dream creation out of carbon fiber and had never met them until the auto show. He absolutely drove out with his wife, and we shook hands in front of this exhibit. It was amazing. There were 5,000 members of the press from 60 countries, and there were 750,000 attendees. That's the metric that makes it the largest auto show in the world. If you're counting attendance, in terms of attendance of press and visitors, the North American International Auto Show is as big as it gets right now. And we had an amazing response. The next morning, this is a YouTube part of the press conference. When you download the slide deck, you can see me walk through a 5-minute condensed version of the press conference explaining the modularity of the car and hear the oohs, ahs, and gasps of the reporters saying that's new and different. The next morning, we were in the New York Times Online. We were linked from Forbes Billionaire Club. And again, we're a group of software developers and others doing this nights and weekends. And we had incredible press. My favorite is the one blown up at the top of the sheet. WIKISPEED is a reminder of the true spirit of the Detroit Auto Show. Some companies are still building mind-boggling revolutionary cars because they can. That's from the Automotive News, and that was awesome. And then, we were in the April issue of Automobile Magazine. And so that's 2011, that's last month. In magazine terms, it's 2 months ago. But we were in a magazine next to an article on AMG's new Gullwing sports car. And we had a 3-page article. So we're riding this wave of positive press, and we're rushing to bring all the tech that makes sense to bring, that we learned in the XPRIZE, to market, to do our part to revolutionize the world of automotive transportation. And this is a lot of why it was so well received. Here's a detailed CAD of what Rob Moorbacher sent over. What's really, really fun about this is it looks absolutely like a race car. That's to have the aerodynamic profile we cared about. This has a very similar aerodynamic profile to that orange shoebox that's almost a verbatim NACA airfoil front and rear that we campaigned in the XPRIZE. It's really low because we wanted to reduce frontal area, and I'll actually talk a little bit about that when we're deeper in the Agile, Lean, and Scrum part of this. And these doors are these crazy, cool show car doors. So you're saying, are you just trying to make another sports car, or are you really trying to revolutionize automotive transportation? This is actually a family car. I'm going to explain exactly how and why. It looks so low and sleek for the aerodynamic profile and low frontal area we care about. It's mid-engine rear-wheel drive for efficiency. That's considered a race car layout, having the engine behind you with rear wheel space. When we drive a normal car into a corner and the engine's in the front, it tries to pull out of the corner. We have nice, big, thick tires up front in all the cars we drive today to combat that. But there's some waste. There's some rub. And we lose a few kilowatt hours of efficiency every time we turn, especially in a front engine car. When you're trying to get over 100 miles per gallon, like we ultimately did, you really care about that kind of thing. So we put the engine in the middle. And you get some of that energy back. You don't lose it when you turn. So we're mid-engine rear-wheel drive, a race car layout for efficiency. We're this low, slick design for aerodynamic reasons. The interior space actually sits for adults, and the storage on this thing holds 20 grocery bags or 6 golf club bags. So it is a thing. But these doors, how could I possibly justify these crazy tricks show cars? Well, the car's wide, and part of the reason is when we go into a corner, and because the XPRIZE was a race for high-efficiency cars. You had to get at least 100 miles per gallon, but then it was also a race. Fastest car wins. Well, once you meet the efficiency metrics. And so we have a wide vehicle so that on the track, we don't have to hit the brakes much going into a corner. We can just carry the speed through because of the width of the car. But we wanted to be able to park in compact parking spaces. If the doors opened out the traditional way, you might door ding your neighbors. So we said, let's have the doors flip forward like a Lamborghini does. What we found is, when you're getting in a Lamborghini, which is also a low car, you got to do this thing. And it's not so easy on your back, especially if you're carrying things. It's not the most easy car to get in and out of. And we're trying to revolutionize automotive transportation, so we don't want it to just be for dedicated enthusiasts and the very young and nimble. We want it to be for as many people as want to enjoy the car. So we had the area above the door open. So you can stand up right out of the car and step out. You don't have to do this thing to get under the roof. Right? And so we have these doors that flip forward so you can fit in a compact space. And we have the roof open above you when the door opens to get out. But then when that whole part of the door opens, it actually would intersect the windshield, so we had to have it open in reverse, which turns out to be a more natural motion to close the door and slightly more ergonomic. And it looks completely awesome. Here's the next CAD by that same guy, Robert Moorbacher of Moore Composites. This is the Roadster. And he's making 2 of these this summer. He's making the car bodies in Germantown, Maryland, at what will be WIKISPEED's 3rd large shop. The Roadster version, Rob is actually going to drive as his daily driven car. We're making a chassis for it here in Seattle, and another chassis in Hillsdale, Michigan, to put under those 2 car bodies he's making. One of them already has a customer. There's a leasee I'll be purchasing it, and the other will be Rob Morbacher. This will be his daily driver in Germantown, Maryland, at 100 miles per gallon. Then, following the success of the auto show, which was January 2011, April 22nd, World Earth Day, Future of Flight, the facility and exhibit associated with Boeing at Boeing Field is an independent, not-for-profit, but it's coupled with Boeing, and they facilitate the Boeing tours. They have their museum with an enormous amount of interesting exhibits. They had heard about us from our Automobile magazine article and invited us to have a display at World Earth Day. So we brought Car Body 2, half of it, in CNC foam so people could step inside. We brought our chassis exposed. We brought a triptych of cars showing how we machine foam. First, it's very pixelated. And then we do a higher resolution pass. And then we gloss it and lay carbon fiber over it. And we brought that triptych and had a set of bumper stickers. And then by this time, a Libre Design CAD company is sponsoring us. And they set up a station. Then we turned around. This is before the events had started. This is at move-in. We flipped their CAD station around, and people got to spin the car around in CAD and see exactly how it works. And this was another enormous success, luckily for us. The executive director of Future of Flight has invited us to have a long-term to permanent exhibit at Boeing's Future of Flight. And what that means is it would be the Rolls-Royce Trent jet engine, the cockpit of an Airbus 380, and then the WIKISPEED 100 mile per gallon car for people to come.
And the carbon fiber fuselage.
Yes. Well, and Boeing, again, the Future of Flight is an independent entity, but associated with Boeing. Boeing loved that we had a carbon fiber body because they're just rolling out their Airbus, their 787 Dreamliner, which is an all-composite plane. And part of their fuel efficiency strategy is reducing weight through composites. And they liked that part of our fuel efficiency strategy was the same thing. And we got to talk about that clearly and show it at Earth Day, just a few weeks ago, April 22nd. So how do we do this? We use distributed, collaborative, Agile, Lean, and Scrum. Here's us at the XPRIZE iterating on the car at the track. In our pit, other people would be checking their tire pressure, we'd be changing the car. We use weekly stand-up meetings, prioritize backlog, and demos, just like most of us here do at our day jobs in software. How we communicate. Now these slides are information dense, so that if you decide to share them with your teams afterwards, you don't have to have me standing here to make sense of them. And you can read through the slides. So here's the background information. Feel free to zoom in and take a picture if it helps. And also the deck will be online. But how we communicate. So we were asked by a class at University of Washington, Bothell, to talk about some of the tools we use in our distributed collaborative team. It's great to say you have a distributed collaborative team. How do you actually make that happen? How do you facilitate it? So our weekly stand-up meetings, we're on the weekly because we're all volunteers, and that fits the pace. So each Thursday at 6 p.m., we all dial into a conference number, and we use freeconferencecall.com. It's free. At our stand-up meeting, we use the standard format, what I did last week, what I'll do next week, and any blocking issues. And after we've each gone through, we then unblock each other. And very often there's the conversation, oh, I heard you were blocked by this. My cousin did that once. Let me put you two in touch. Or I've got a few ideas. And they'll stay on the line and communicate. Then with our international team, we then use Skype, again, free. Then on the daily, we have an email distribution list, again, free, provided by Google Groups, where we keep all the team up to date on what's going on daily. So we post pictures, and we post updates, and we email the backlog to the team. We use a Google Doc, and then we screen cap it and email it. So we have push and pull communication of the backlog. They can go to the Google Doc, and they can edit it and say, this is now pending review, or I believe this is done. Or I discovered these additional work items. Or they can view the push communication that's been emailed to them. We intentionally avoid planning more than 2 weeks out. Now that said, we have a very clear vision of end states, of different final deliverables, different cars. And so if A sprint, if a 2-week chunk of time for us, has an update to the braking system, a adjustment to the Ackerman angle of our steering system, and 2 more degrees of preheated fuel. We know we're not finished with the entire project, even though we avoid planning more than 2 weeks out. And we avoid planning more than 2 weeks out because in that 2 weeks, chances are we really change what we're going to do next because we learn so fast. So if someone comes and presents to WIKISPEED, I have the 6-month plan. How long did that take you? Oh, only 16 hours. That was 16 hours you could have spent working on what we know about now, because you know by the time you've done the next 8 hours worth of work, that's all going to change. So we care about that very much. We want to avoid that waste. But the trick is that we know where we're going. We know the end state is driving these cars around at 114 miles per gallon on the highway and 104 miles per gallon in the city. And so we avoid having releaseless builds. Then Google Docs for real-time collaborative documents. It's great. I can be talking to someone in London and someone in Ireland through a Google Doc at the same time, and we'll have multiple cursors, and they'll be different colors, and we'll be creating a document together, like a grant application or a certification process submittal, or a letter to one of our micro-investors updating on status. And we can see each other's cursors all at the same time, and it helps mitigate the fact that we're a distributed team. We get some of the advantage of having people thinking very different ways and multiple time zones, and yet we can collaborate fairly rapidly, and we use Google Docs for that. Again, it's free. Then we use a single cloud store of version documents. The really neat thing about Google Docs is it enables us to trust the team to a higher level. I can put a sensitive document out there and share it with the entire team, many of whom I've never met face-to-face, and it's versioned. It says who changed what when, and we can always roll back. So I don't have to worry about someone typing over everything if they had a really bad day, which has never happened. Because I would know who did it, and I could revert. And because of that, we're able to responsibly trust the team. We get to go into that. There's a whole slide about the value of that and how to do it well, we think, what we learned as we tried to do it. So we'll dive deep into Trust Your Team soon. Then we use Facebook and LinkedIn for team and public status updates. What that lets us do is we don't have repeat of information sharing. If we do a car test in Seattle and I film it and I put it on YouTube and post it on WIKISPEED's channel, everyone in the team gets to see it and understand the current state of the evolution of the product, and then the people who are following us from outside the team get to see it. So it's built into the same marketing channel. When new team members join and they fan facebook.com/WIKISPEED, we get to know who they are and see their profile. They can still send an email introduction to the team saying who they are, but also they've introduced themselves to the world, and also the people who are interested but not ready to join the team are then able to fan our Facebook page too. Same with LinkedIn, so we avoid having multiple repositories. Then we use Dropbox and SkyDrive for sharing large files like our cat, and again, that's free too. And then YouTube to share videos of tests and events with the team. The principles of this approach. This is the secret sauce. If you were going to take a picture of a slide, I'd say this one. This is what we found worked when we were porting Agile, Lean, and Scrum to far outside software to actually rapid prototyping and micro-manufacturing. 1, by minimizing cost to make change, we innovate quickly. Now, that's changes in team members, that's changes in goals, that's changes in machinery, and that's changes in materials. If a team member comes in and they know all about carbon Kevlar combinations, we want to be able to incorporate their knowledge and start using carbon Kevlar combinations quickly. The entire aeroshell body is a module, so we can. If we have a team member join who has deep expertise in aerodynamics, which we did, the gentleman who founded GM's aerodynamic test facility and led it for the next 40 years joined the team at the North American International Auto Show. And he had brilliant ideas on how to refine our body. We didn't want to have to build a whole new car. So the modularity of the drop-on body enabled us to quickly take advantage of his aerodynamic smarts. If a team member leaves with a particular skill set, so we have to revert, maybe we didn't knowledge share as well as we should have or could have, we want to be able to recover from that quickly and inexpensively. By minimizing cost to make change, we're able to roll with all of that well and quickly. And that's intended from Agile. And then goals. So the XPRIZE, the scoring criteria originally was get 100 miles per gallon and then win a race. And the race was going to be downtown Manhattan. And they were closing the roads and having a road course with long straightaways and then tighter 90-degree hairpins and then long straightaways. That takes a particular type of car to get 100 miles per gallon in that situation. You want to optimize your suspension for that and optimize your drivetrain algorithm for that. Then the XPRIZE said, you know what? It's going to be a cross-country rally, and it's going to be on public highway. That's a very different type of vehicle, again, when you're trying to compete at the top and win. We were able to change our modular structure by swapping suspension components in about the time it took to change a tire. Other teams had to build a new car. Then finally they said, it's going to finish at Laguna Seca in California. For those of you who are a car person, there's a turn called the Corkscrew, where you go up and it looks like a mountain, and then you have this tight left-hand turn, and you descend really, really fast, and then have to turn right with no loading. And we're thinking, are you serious? We're trying to make commuter cars. That requires a genuine full-on race car just to stay on track. So again, we iterated our suspension, and other teams withdrew from the competition. Finally, all of the races ended up being at Michigan International Speedway on their speed oval, their road course, their skid pad, and then also they have a drag strip which we use for lane change tests, going to 55 miles an hour and avoiding an obstacle. By loosely coupling modules, we make changes in parallel. It's very frequent that we'll come into the shop on a Thursday night, 7 o'clock, and we'll split the car out into its component modules. And we'll have people working on the suspension system, people working on the drivetrain, people working on the emission system, people working on the interior, on the headlights, on the electronic control mechanism, and they're able to do it all in parallel. And in fact, we can have more than one suspension system being developed at once per car because we have modules, just like you would find that advantage in a software team. By working collaboratively in a shared space, we unblock quickly. When we're in a Scrum room, or when we're in the WIKISPEED shop, if everyone is in earshot and eyesight of each other, you get to see the body language change when someone hits a block. They don't even have to say it yet. They might be going through a really difficult problem, and maybe they're in a pair, and the pair starts getting quieter. They haven't yet said, look, we need a swarm, an event from extreme programming. But we'll notice, because everyone's within eyesight and earshot of each other, and the team will swarm. We wouldn't know that if we weren't in a collaboratively shared space. And what we found is every time a pair had a blocking issue, the team swarm was able to bulldoze it that same day. Every single time. And we were dealing with some really tricky problems, solving some things that have never been solved before, like building 100-mile-per-gallon cars. Still, from extreme programming, pairing and swarming worked very well. By first automating tests, we quickly know if we've improved. We started with a red light, green light dashboard saying 100 miles per gallon or higher on the city cycle, 100 miles per gallon or higher on the highway cycle. These safety tests must have these requirements to campaign successfully in the XPRIZE. And we built those in terms of regression tests. So we did test-driven manufacturing. I guess it'd be TDM. What we would find is when someone brings in a module to say, I've made this 2 kilograms lighter, or the turn signals now start by blinking on instead of having a 1-second delay before they start blinking. We would get to see, did they interrupt any other systems in a negative way? So we quickly knew if we'd moved the entire bar forward, or if we'd moved forward on a few fronts, but actually back on 2 other fronts. So we got to kill work that would have actually been damaging quickly and be moving forward very fast. Tests are success criteria. There was a brilliant talk yesterday from who did measure or not to measure in HR. It was Bruce Weingarten and Larry Cross. And they were taking on the issue of what to measure and how to reward an Agile Lean Scrum team or any team in an organization. And what about measuring team performance? What we found in WIKISPEED is that if what you measure is the success criteria, miles per gallon, safety rating, top speed at 100 miles per gallon, braking distance, weight of the vehicle, etc., etc. Everyone cares about the metrics because they're the metrics that are going to get them to win $10 million. Or they're the metrics that are going to have them drive a car on the street that they helped build that's revolutionizing automotive transportation. So we didn't measure things like number of bolts or thread count of bolts, which was maybe similar to lines of code. We measured the success criteria, and that way everyone cared about the metrics. And when a metric went red, everybody cared. And when a metric went green, everybody jumping high-fived each other. It was kind of a big deal. Team morale is a multiplier for velocity was the number one takeaway. It's number 6, so that I get to say it really loud. It wasn't just that it got a little bit better or a little bit worse when the team had a really high motivation day or really low motivation. It was actually an order of magnitude. It was at least a multiplier. All we were doing by applying Agile, Lean, and Scrum was keeping team morale high, which was actually the velocity multiplier. That's not entirely true. There's some velocity embedded directly in Agile, Lean, and Scrum, but a large part of it is making sure people are never frustrated or rarely frustrated and that they get to share successes. Iterations and stubs make for constant successes. The first version of the suspension was made of wood. We couldn't take it on the track, but the car now sat at the correct ride height. That was a big deal. This chassis we'd made that had an engine in it on a test bench was now sitting 4 inches above ground, which would clear speed bumps. We were ecstatic. We high-fived each other. Motivation went through the roof. And we hadn't even finished the suspension system. We didn't have a working V1 other than a stub, this wooden setup that held it at the correct height. As it became our first steel suspension setup, it was exciting again because now we could drive it a little bit. And as it became aluminum suspension, we were much more excited again because now it had the correct geometry during bounce and steering scenarios that we cared about, and it was far lighter, so we were getting closer to our fuel economy goals. So we got to celebrate every iteration. And then stubs. The first parking brake, we knew we had a parking brake that we had to add. And it's actually a little bit more of a tricky problem than a lot of us had realized. A normal parking brake on a car, the brake pads float on the brake rotor. They touch the brake rotor even when it's not engaged. That means you're losing some energy as you drive along without that brake on. We didn't want to have that. We couldn't when we were shooting for over 100 miles per gallon. So we had to ask intelligent questions online and say, we have this nuanced problem about a parking brake. Who knows about that? And we attracted deep nerds, which is what we needed to help answer those questions. By asking nerdy questions, we got the right kind of nerds. And then, while that was being developed, we finally knew what size it was going to be and where it was going to go. So we put a cardboard box there. The team was ecstatic because they got to build around the parking brake now. Before, they were nervous to be in that whole area because they didn't know what was going to go there and they didn't want to redo their solution just to make room for the parking brake. Now that we had a cardboard box sitting there, they knew they could build around it. They got to celebrate the stub being put in and velocity improved. You guys are awesome. How we did it. So number 3 on that list was modularized tools and inventory and collaborative work areas. This is a picture of how our XPRIZE shop here in Seattle looked just before the XPRIZE. So this is in 2010. There's our chassis at that time. We had a different roll bar system, and it had these 2 hinges for gullwings going this way that aren't attached here. It's just the chassis visible. All our fasteners were in one place. So if someone said, I need, I think, a bolt or a self-tapping screw, or I don't know, we could just say, fastener shelf. And every fastener we have is there. If we don't have it, that means we need to go get it, or they can use what we do have. So it answers the question really fast. So someone's not blocked for a while saying, I wonder if we have X, Y, or Z. Then behind them is the safety shelf. When we get a new volunteer, we need them up and productive within minutes. Some of them were race car engineers. Some of them worked for NASA. One of them founded the material science lab at MIT. Many of them had never changed their own oils and were in it for environmental reasons. So we have this wide spectrum of talent, and we need them to be productive almost immediately. So orientation gets to go this fast. They walk in the door, and I say, on your left, you have the safety shelf. All safety equipment and spill cleanup is there, and our material safety data sheets are there. That's all I have to say. They can see in clear, transparent bins that there's face shields, a hard hat, and they go, okay, I guess there's things that might require that. I'll pay attention when someone uses it. You don't even have to take time explaining. They see earplugs, they see hearing protection, they see dust masks, and et cetera, and spill cleanup equipment. Next to it's the snack shelf, equally important. We had a guy, the lead UI designer for Gmail, who was now in San Francisco. He flew up for 10 days on his own bill, unpaid vacation, to work in the WIKISPEED shop, and he didn't leave. He ate all meals, Kellogg's Special K cereal bars from the snack shelf, and worked straight through, heavily caffeinated. It was completely epic. I wouldn't recommend it, but it worked. Saved the day. So here in green we have our sprint planning board. Now it's about 4 times that size because the team has grown and we move tasks that fast. Then we have the power tools shelf where all power tools are. Now this has a good analogy in software in that everything's visible at once and the consumables are next to the tool. So when someone new who's never used power nibblers before, which are used for trimming sheet aluminum, they see them in a clear, transparent bin, and it's labeled power nibblers. And they go, okay, now I even know what this thing is, and I know you have it. And all power tools are within eyesight of each other. And then the consumables are right below. So under the drill bin are drill bits. And then there's a bin inside the drill bits bin labeled drill bits that need to be sharpened. And so they know. We don't even have to explain it. And they might not have ever even drilled a hole before. And in the end of the day, they're drilling holes. Our milling machine is the same way. So that's one of our more complex pieces of machinery, and it's very, very useful. We have everything out that makes a milling machine or that use a milling machine visible. So people walk by and already they start to build the mental context of what it takes to use this tool because every part of it's there. Then they'll walk by and see 2 people using it. And they'll get to have an idea of what it takes to make that machine do its job because we're all in this collaborative work area. You can see everybody. So by the time the person goes home that night, they have some idea of what you use with a milling machine and how to use it. And all the power tools we have, all the power tools we don't have, all the fasteners we have, they're aware of our inventory, and the entire scope of work that's going on. It's the same value of a scrum room, where everyone's together constantly sharing information. Then, the next day, they might be in a pair with someone who's used the milling machine before, and they'll go through all the processes. By the 3rd day, someone who has never drilled a hole in something can be leading a pair of the milling machine. And that's one of our more complex tools. It goes that fast. And so some people say, do you have to be the right type of mind to adopt Agile, Lean, and Scrum well? Is it about the team more than the process? I can say, by cycling through more than 100 people in the WIKISPEED shop, no, it's not about the people. It's not about whether the person is capable. They all adopted Agile, Lean, and Scrum. Many of them didn't know that's what it was called, but they knew they were building a car really, really fast according to this different set of principles and way of doing business than they'd done it before. Modular inventory, to pound that point home. Whenever possible, tools are visually next to their consumables. In software, it would be if you have a set of interfaces that all solve a similar problem, that you group them with similar naming convention. Same idea. It's that you're aware of the entire scope at a glance. And so this is applying that same idea physically. Then like tools are with like tools. So bolts are with bolts. We wouldn't want to have 2 locations of bolts because then I couldn't say it's in one of these. I wouldn't want to say it's in one of these 2 places. I want to just say bolts bin and they're aware. Fewest possible categories all within sight of each other. So if someone stands here, they can see everything we have and don't, and they don't have to go anywhere. This is part of that keeping velocity high by keeping morale high because there's no time spent trying to find something. Minimize time spent doing anything but creative problem solving is the mechanism to high morale. One of the mechanisms for high morale, which is the whole secret to high velocity. A brief history of Lean. So Lean is the common sense principle, use less stuff. Some people in this room might be really, really deep in Lean and might be able to lead an entire session just on this aspect. But it's the common sense principle, use less things. Then in the end of the 1800s, early 1900s, the firearms industry in Europe started doing interchangeable parts. So now they could repair a gun without having to make one-off parts for it. They could pull a pre-made part out of a bin. It dramatically improved the repair and maintenance process of firearms, and then ultimately the assembly and manufacture. It started happening in other machinery as well, and Henry Ford popularized this process and became famous for it. Not just interchangeable parts, but other applications of lean. He found other ways to responsibly use less stuff. Less colors of paint is the famous example. You can have a car in any color you want as long as it's black. Henry Ford was quoted as saying. Then, in the late 1940s, early 1950s, Japan had the unique opportunity of rebuilding its entire manufacturing base, infrastructure, and supply chain. They had sent essentially the equivalent of consultants to study the Henry Ford method, and then other people who were less known but practicing the same principles well. Brought these back to Japan and built the entire manufacturing infrastructure according to these principles. So it wasn't being retrofitted on existing manufacturing lines, they were being built around these principles of use less stuff. And then the new supply chains were built around the principle of use less stuff. And they were getting really good at just-in-time. In the 1960s, this was packaged into Lean Six Sigma and exported back out to the West. Manufacturing now is still getting enormous benefit from Lean Six Sigma. Folks with their Lean Six Sigma black belt are still extremely valuable in revolutionizing manufacturing. I guess what I'm trying to say is that's how slow it's going. This is tech from the 1960s that all goes back to the most basic human principle, use less stuff. And they're still getting dramatic gains from it. In fact, Ford is being applauded right now for doing it better than GM or Chevy, and this is in 2011. Meanwhile, in the 1970s, software said, hey, can we do any of this stuff that's going on in manufacturing? Does any of this apply back to our software teams? And they start trying lean-ish principles, Six Sigma-ish principles, start doing iterative process, and they find it works pretty well, and they decide to make modifications to it, change it, try alterations to the process. In automotive manufacture, if you want to make a small change to your line and the way your line works, you wait 2.5 years for the minor model change of the vehicle you're building. If you want to make a major change to your process, to your line, you wait 5 to 7 years now for the major model change, for the model change. If you want to make a very dramatic change to your process and flow that might change the factory, you wait 30 to 40 years until the factory is end of life. If you want to make a change that affects your supply chain in a dramatic way, you wait until your grandkids can make that change, because that's how long those relationships last, and is directly linked to that American manufacturers still have far more profit margin in large heavy vehicles than light nimble vehicles when Europe and Japan don't. Supply chain decisions made with foundries